Here's a concentrational momentum problem that we'll do next year. What this one's about is about a firecracker. I don't know why the firecracker's around, but here's my firecracker that is, and it's just sort of sitting here at the origin. And suddenly what happens is the firecracker explodes. And it explodes into 3 pieces as described here. 2 pieces here that both have a mass m. One goes this way, sort of on the negative x-axis or west, with some known speed and some mass. So this known speed is given in the problem. Another firecracker, another piece of it rather, piece 2 of it, goes straight down, so straight south or along the negative y-axis with the same mass as the other one and the same speed as the other one. So 2 pieces with identical masses explode off the original firecracker. One moves down this way with speed v, the other one moves out this way with speed v, and off they go. A third piece, which has twice the mass of either of these, so a 2m over here, not just an m, flies off in some direction with some speed v and some theta that they want you to find. So the question here is, what is v and theta? They didn't tell you any information about the direction it'll fly off in here. I've just sort of guessed that if a piece flies over to the left and down like that, the third piece, if 2 pieces do that, the third piece must sort of go up and to the right, but it's just a guess. And the guess is okay, because I'm just going to leave this generally as an angle theta, which can be anything. Now fine, if theta just comes out to be something between 0 and 90, that means the piece did fly off in this direction, but theta is free to be whatever it wants. That's the algebra and the physics will dictate when the problem is done. And of course the speed v, which I have no idea what it is. Okay, so what we'll do in this problem here, it is a 2-dimensional problem. So we'll say the initial x momentum is equal to the initial is equal to the final x momentum, and we'll say that the initial y momentum is equal to the final y momentum. So it's going to be a 2-dimensional conservation momentum equation, and note that these 2 equations are coming from the vector form p initial is equal to p final. So these 2 are what often branch off from this vector equation. Remember, vectors contain x, y, and z components in them no matter what we're talking about here. So I just sort of branch it off and say p initial x is equal to p final x, p initial y is equal to p final y. So those are the 2 guiding equations I'll use to sort of get this problem to work out. So then let's just fill in and see what we get. Let's do the x first right here. We'll fill this one in first, I guess, because it's sitting right here ready to go. So what initial x momentum do I have? Well, before the collision, I don't see anything moving at all. I just see this firecracker sitting here, so there's no x momentum before not the collision, but the explosion. After the explosion happens, this is the after case over here, so this is the initial scenario over here, this is the final scenario over here. So after the explosion happens here, I see 2 possible x momentum. I see this one going off in the minus x direction, so I'll go ahead and put in here a minus m times v. That's its momentum that it's carrying away. And I also see an x component of this one's momentum here. In particular, the mass of it is 2m, the speed of it's v, but along the x-axis it'll be a v times the cosine theta. So this is the conservation momentum along the x-axis after the collision. There's the piece moving to the left. There's the piece, the unknown piece that has some unknown angle and direction, moving off in some direction, but no matter what direction it goes in, its x component of momentum will involve the mass times the v cosine theta. Likewise, I can do the same thing for this one here. So this is the x momentum right here. I can do the same thing for a y momentum now. And in particular, once again, before the firecracker explodes, there's no momentum at all because it's just sitting here, the v of it's 0. So there's no momentum before the collision, the explosion happens. And after the explosion happens, well, I've got this piece moving down along the negative y-axis. So this will definitely be a minus m times v going straight down like that. And I also see a y component of momentum over on this side over here, moving straight up, I guess. So I'll call it 2m times v times the sine of theta. So that's the momentum I see after the collision. And this is y momentum right here along the y-axis. So again, just to highlight what's happening here, is that it is a 2-dimensional collision. The thing sits here at rest, but after it explodes, it goes off in 2 directions, and this second direction here has 2 components. It has a Vx that way, it has a Vy that way. So I've used some trigonometry and vector things to figure out what those components are, and from that I'm able to form my conservation momentum equations right there. So, well, what's the next step? Well, the problem gave you what m is and what the speeds are of those individual objects here. And so what you have here is, if you look at it here, you sort of have 2 equations and 2 unknowns. So, of course, the 2 equations are this one and this one, 1 and 2, and the unknowns that you have are your v and your theta. So you just have to figure out some sort of way of solving for them. What I would recommend doing is something like you could sort of work on the first one here like this. If you solve this one a bit here, the m's are going to cancel away, something like that. So you get something like v is equal to 2 times capital V times the cosine theta, something like that. And if you work on this one, again, the m's will cancel away here, and you'll get something like v is equal to 2v times the sine of theta, something like that. And now what you can do is if you just sort of just divided these two equations here like that, you'll get 1 is equal to, looks like the cotangent of theta. And you can sort of carry that on at that point, but looks like your angle will come from that, and after you get the angle, then you can plug in here either one of those equations there to get what the speed is going to be. So that's the way that problem will come out.